Wilcoxon signed rank test. So this Wilcoxon signed rank test usually tests whether the median of paired differences differs from 0, and is usually the non-parametric alternative to the PAT test. So usually use this for either paired sample, one sample, or matched pairs. So we explained previously in PAT test that paired samples are observations that are paired. A typical example can be patients that take a drug today and the next 2 weeks they take that same drug just to find out whether they are actually recovering or not. You can see it's still the same patients, the same drug, but at different times. So this is a PAT test. But if we feel means that to take the drug and means that to take the drug, then this is an independent sample t-test case. So the situation whereby your data doesn't meet the assumptions of the PAT test, you fall back to the Wilcoxon signed rank test. So how does it work? So this is just how you can calculate it manually, but we already have functions in R that can do this for you. So first of all, you just calculate the difference between the pairs. So what is the difference between the pairs? Let's say those the BP of a particular patient was this, in the next 2 weeks it was that. You calculate the difference, then you now remove the 0 differences, then you rank the absolute value of these differences. Then you now assign positive and negative signs to rank based on differences. Then you sum the positive ranks and the negative ranks together. So assigning rank means that you are going to be assigning, if you find out the difference between pair 1 and pair 2 is positive, you put it. If you find out the difference you are getting negative, you put that negative rank. And you sum the positive rank and the negative rank. So you have to find out the test statistics is the smaller of the positive or the negative rank. So this is just to show you how it works, but in real life you will just actually not going to be following this procedure. You are going to be using R to actually calculate it, which I'm going to show you in the lab. So what are the assumptions? So first of all, paired observations or single sample. Then the differences are also independent, and the differences come from a continuous or ordinal distribution, and the distribution of differences is symmetric around the media. So these are simple assumptions which is actually clear as you can see it. So symmetric assumption is also important but often overlooked. So what do we mean by symmetric assumption? So the simplest way to know symmetric assumption is that the mean of that particular data is equals to the median and also equals to the mode, which means the data is actually what's symmetric. So the values are actually equally spread on both sides, or on both sides of the center. So when you actually plot it, you find out that the values, the right hand side of the data is similar to the left hand side. So this is usually a strong assumption of the PAT test, but usually overlooked in terms of the Wilcoxon signed rank test. So this is the hypothesis. The first of all is that the median difference, this is for a two-sided test. Their median difference is 0. That means they are actually equal. There is no significant difference between their median. While the alternative hypothesis, there is a significant difference between their median. In the one-sided test, the median difference, in one-sided test, we're using just one data or one sample data. So the median difference is less than or equals to 0, or we can say the median difference is greater than 0. That is between the hypothesized mean. So interpreting results. So we have the V statistics, which is the sum of the positive or the negative ranks. Then we also have the p-value, which is the probability of observing results if the null hypothesis is true. And we also have the pseudo median, which is the median of all pairwise averages. So your decision rule is to reject your null hypothesis if the significant difference usually exists, or you fail to reject your null hypothesis if insufficient evidence of difference shows. So an example scenario, a clinical trial whereby the blood pressure is measured before and after treatment. So 15 patients with non-normal differences. So does treatment reduce blood pressure is what we're trying to find out. You can see this is a paired observation. 15 patients are being tested before and after treatment. I want to see if this particular treatment reduces blood pressure. So why are we using the Wilcoxon rank test? We should know the reason before we start applying it. First of all, it is a paired data. Also, we have a small sample size. I talked about n less than 30 earlier on, but you can still use it for a large sample size if it is not normally distributed. Then also, we have interest in the median change.